Um, Welcome to this class, guys. So this is a recorded video for two of the derivations in wave optics, and these are very basic derivations that you should be knowing about. There are various concepts about refraction and reflection that go on in this derivation, and this is just application of those things, but in the wave optics point of view. Okay, so the first derivation is from the topic in your book 10.3, and the thing is called refraction and reflection of plane waves using Huygen's principle. So first we do refraction of plane waves sorry, using Huygen's principle. Okay, so we will do refraction first. So how do we do this? So what we do is we consider an interface. So for refraction, we know there is always an interface between the two media, right? So we have two mediums, medium 1 and medium 2. So it's not mediums, it's media, sorry. So medium 1 and medium 2. So this is medium 1 and this is medium 2. And the two medium have different refractive indices. So their refractive index is different, basically. So that means a electromagnetic wave or light coming from medium 1 will show some kind of bending in medium 2. Similarly, from a ray of light or a wave of light, whatever it is, coming from medium 2 will show some kind of bending when it goes to medium 1. Okay, now let us assume that medium 1 is a rarer medium and medium 2 is a denser medium. So now we know in wave optics what the most important thing is: a wave front. So let us say this is a wave front AB. So we know from wave fronts there are wavelets being created, right? So every wave front is a plane where all the particles vibrate at the same phase. So all the particles in this wave front are in the same phase. So there is a wave coming like this. Let's say this is one wave at A. I'll not do multiple waves in between. I'll just do two waves, one at B here. Right? So now what we can do is we can put a normal somewhere here. And we can trace back the direction of this light ray. So if there was no medium in between, if there was no second media, the ray of light would come this way. This wave would move this way. But now it'll show bending towards the normal. Right? I don't think this is very difficult to understand. So let's say the wave reaches a point E. That is all according to your book. Right? And at the same time, this wave that is starting at the extreme end of this wave front reaches this point here. So this point is labeled as C in your book. So the time in which this wavelet that is generated at this point of a wave front reaches E, at the same time the wavelet that is generated at B reaches C. Okay, so now let's say the speed of the wave in this medium is v1, the speed of the wave in this is v2. So we can say that this is v1t and this is v2t, because we know velocity equal to distance by time. So to find the distance, it is v into t. So we know that these distances are the same, like these two distances are the same. Light is traveling, like it's not the same, but it's traveling at the same time. So in v1t, this wavelet is reaching this point C here, and at time t again this wavelet at A is reaching point E here, right? So we have also already specified the velocity of the wave in the two media, right? So now let us join this point here, this with this. We joined these 2 points. Now this is obviously 90. This is the angle of incidence I. This is the angle of refraction R. Right? So this will be 90 minus I. This one will be 90 minus I. So again, this one will be I as well. So if you use laws of geometry, this will be I. Now since this is R, this will also be R. I want you guys to work the geometry out yourself. So this will be 90. So you can just think about why this is R, right? So this is also 90 here. Now we can just simply, what we can do is we can use Snell's law. So for Snell's law, we need sine I. Sine of angle of incidence is some people have perpendicular by base. So perpendicular is BC here. For I is BC. By base is AB. It's hypotenuse. Some people have it's hypotenuse. Hypotenuse is the side opposite to the 90 degree. That is AC. Then we have sine R is some people have again perpendicular by hypotenuse. So perpendicular in this case is AE divided by hypotenuse is the same thing, AC. So now we know that the refractive index of light coming from medium 1 to medium 2 is sine I by sine R, which is basically BC by AC divided by AE by AC. AC cancels off. You get BC by AE. So I'll rewrite it here somewhere. 1, 2 equal to BC by AE. So now we know what is BC. BC is nothing but V1T divided by AE is nothing but V2T. TT will cancel. This is V1 by V2. That does make sense because we know that refractive index of 1 with refractive index of 2 with respect to 1 is nothing but refractive index of 2 divided by refractive index of 1. And we know that refractive index is speed of light in that medium, the speed of light in vacuum divided by speed of light in that medium, whole divided by speed of light in vacuum by speed of light in that medium. This will cancel off. Sorry. So it is rho 2, that is C divided by V2 divided by C divided by V1. CC will cancel off. This will be V1 by V2. So this is basically Snell's law, and this is basically the proof that laws of refraction does apply to waves as well, right? So these are waves and laws of refraction apply to waves as well. So this is just the proof of that happening. So this is one derivation that you should know, and I believe it is actually very important. Okay. Yeah, I think this is clear. If it is clear, I can move on to the next topic. So yeah, so what we can do is you can just revise this. I'll send you this derivation as a PPT as well, or a PDF if it's fine. And what you can do is I'll give you a little bit work, a little bit of a task for you. And what I want you to do is I want you to derive the same thing, but when the wave moves from a denser to a rarer medium. So I want you guys to derive the exact same thing, but now the wave is moving from a denser medium to a rarer medium, not rarer to denser. So this will be opposite of this, right? So the wave will bend away from the normal, etc., etc. So that will be there. So if you get time, you can just solve that and find the derivation and prove the laws of refraction does work on both the ends. So if you can do that, that would be amazing. Can you follow? I think you can. So what we can do is we can go to the next topic, and the next topic is proving the law of reflection. So reflection now. So to prove the laws of reflection, the most simple thing would be to assume a plane mirror. So I'm assuming a plane mirror here. The lines that I'm drawing is to show the coating. Again, I consider a plane wavefront like this. Let's say this is AB, and there are two waves we can consider. You can consider as many waves as you want, but I consider only two. So one at A and one at B. So now we can draw a normal here. Let's say the velocity of wave in this medium is V, and now what happens. Now the ray of light will suffer reflection and will reflect somewhere here and reach a point B dash, right? So at the same time, let us consider that the wave at B goes and reaches a point on the mirror at A dash. So that is at the same time. So if you just think about it, AB dash will be equal to BA dash, right? because at the time where the wave at A reflects and reaches B dash, at the same time the wave at B reaches A dash, right? So now again here at the phase A dash as well, there will be reflection. I'll not draw this to scale. So the ray of light will go back. Sorry, not this way. So now we can say that the next secondary wavefront is somewhere at B. So if I draw a locus here, if I draw a circle here, I can find the next secondary wavefront. So the first wavefront was AB. Now after a certain time t, there is a secondary wavefront that is created at B. So if I draw a circle around this now, I'll get the wavefront. So you know what is wavefront? Wavefront is the position where all the particles are in the same phase. So now if I say from A dash, I draw a locus, I draw a tangent to the point B dash. So this represents the tangent of the locus of the points of the next wavefront. So I'm drawing a tangent to B dash, which is the tangent to the next wavefront. So this is the first wavefront, 1 AB. The second wavefront is AB dash at B dash. Next wavefront will be formed at B dash. So if you draw a circle there, you'll find the next wavefront. Okay. So now you know that this angle is 90 because it is the angle between the plane wavefront and the wave. This angle will also be 90 because it is a tangent to the circle that will be eventually be the next wavefront. This angle is I. This angle is R. So again, this angle will be I. Sorry, this entire angle will be I. That is laws of geometry. And this entire angle will be R as well. So now sin I is some people have. So perpendicular by hypotenuse. So perpendicular for this will be A dash B divided by hypotenuse is A dash. Then sin R will be perpendicular by B hypotenuse again. So that will be AB dash. That will be AB dash divided by A dash. So now you know sin I by sin R. So let us consider this medium to be air. Let it be air. Sin I by sin R will be A dash B dash divided by AA dash into AA dash divided by AB dash. Okay, so this will become, sorry, it's not A dash B dash, it is A dash B only. So this becomes A dash B divided by AB dash. So you know what is A dash B? Why am I writing A dash B? Yeah, it is A dash B. Okay, A dash B by AB dash. Okay. So now A dash B. So A dash B is the distance from B, that is the point on the wavefront, to A dash, that is the point on the mirror. So now we know that velocity of wave in the medium is V, and we know that at time t equal to 0, that is the initial point of the experiment, the wavefront was AB. Then there were two waves, at A and B and at B. And I said that at a certain time t, the wave at A reached the point B dash. Within the same time interval, the wave at B reached A dash. So you can say that this one holds true. Also, you can find this as V into t, because it is velocity into time. So velocity equal to distance by time. You know velocity is V, time is t. So the distance will be velocity into time. So A dash B and AB dash are exactly the same. A dash B and AB dash are exactly the same because it is the distance traveled by the wavefront or the wave or the wavelet, whatever you want to call it, at a certain time t. That will be the same because there is no two medium here. There is just one medium and a plane mirror. So there is a reflection to the same medium again. So you can say that this is A dash B divided by again A dash B. They are the same things, equal to 1. So now this holds true for reflection.